All right. Sorry for the delay there. I'm still paranoid that I forget to start the recording. All right. I hope everyone can see the screen okay. Let me know if you can't. This is where we were last time. We were talking about the idea of pointers, and every type in the language can have a pointer type. So if you have an int, you can have a pointer to int for keeping up with where that int is stored in memory. Same with all the built-in types and with other types that we'll learn about later. Including pointer types. And that's kind of what we're showing off here. This is our first look at pointers to pointers, and we'll revisit this a couple of times. It's not really that complicated of an idea. The notation maybe gets a little tricky, but here's how I try to think about it. If a pointer is a good way of being able to look, let's say a pointer to an int. If a pointer to an int is a good way of being able to look at that int, and since you know where it lives in memory, you can change it. Well, a pointer to a pointer is a good way of being able to look at where that pointer points and be able to change it, be able to make it point somewhere else. And that's kind of what this example's doing. Here, we've got the same setup we had at the end of class on Tuesday. I make two ints, I put a 5 and a 10 in them, and this matches the picture over here. So as I read through this, sorry, I made my mouse pointer really big, at least I tried to. And I know I point with it on the slides. Hopefully that will make it a little easier to see. I make a couple of pointers that point to each of those ints. And then I made a couple of pointers to those pointers. And we're just showing off that it's kind of the same idea using these pointers to pointers down here. I can look at, I can use these pointers to ints, I can even change them. And that's what we're doing now. In fact, this first line changes this pointer right here. How does it do it? Well, let me read through this, and then the next slide kind of shows a picture of the result. This says, give me the address of B. What do you want to do it? So that's the address of this B up here. That's a pointer to B. Take that pointer to B and put it in whatever PPA points to. That's sort of what you can read the star as. It's the dereference operator for pointers. So it says take whatever PPA points to. That's, well, PPA points to this PA pointer, and assign that to the address of B. So that, I'll skip ahead to the next slide. That makes this PA pointer point to B. And then I've got the picture goes ahead and shows the next step. Once I've done that, what do? Well, I take whatever PPA points to, follow that. That's what this first dereference operator says. So I follow that to PA. And then what do? I dereference that. That's this outer dereference operator. So follow whatever that points to. And now that's B up here. And then I just add 1 to that. So backing up a slide, that's what takes B from 10 up to 11. Questions before we move on? I have one more example to show this off, and again, we'll revisit this later, but pointers, if pointers are useful for changing the value of primitive types, being able to keep up with the address of pointers themselves can sometimes be useful for being able to manipulate what's held in a pointer. One more example, we're starting from the same setup here, but the code down at the bottom is different. Here, I'm changing what one of these pointers to pointers points to. Sorry, that's hard to say, but it's easier to see in the picture. I'm saying take the address of PB. Well, that's the address of this guy right here. What do you want to do with it? I want to store that address in PPA. So the first thing that's going to do is take this pointer and make it point here instead of where it's pointing. And then I do almost the same thing we did before. Let me move to the next slide because it shows that first result. And then this next line says, take PPA, the first star or the inner star says follow that, go to the thing it points to. And then that's a pointer. The outer star says follow that pointer to the thing it points to. And then what do you want to do with that? Well, minus equals 1. So we subtract 1 from whatever's in that integer of memory, which happens to be B. So this is just showing, kind of trying to get a little more exercise with the pointer syntax. Remember earlier in this lecture, we learned ampersand as the address of operator. That's how you get the address of a thing, including potentially the address of a pointer. And the dereference operator, a way of getting the thing that a pointer points to. There's really, and I'll revisit this in a moment, but there are really two uses of the star operator that we're learning. The dereference operator, for if you have a pointer, it lets you talk about what it points to. And what we're doing here, it's still notated with a star, with an asterisk. But this is the type operator for making pointers. So if you see a star in a variable declaration, it's describing the type of that variable. And I wanted to point out one detail here. We already saw to define a pointer type, you have some regular type followed by a star and then the variable you wanted to declare. In C, that int, you can declare multiple variables on a line. That int applies to all of the variables, but not the star. The star just goes with the next variable that's being declared. So this line would declare a pointer to an int named x, but y would just be a regular old int. If you wanted y to be a pointer, you'd have to put another star for it. This is, it's kind of unfortunate that the language works this way. I think this is an easy place to get confused. There's a reason that it works this way, but that's something that, that you should keep in mind, that even though the int part, or whatever the type at the start is, applies to all the variables, each variable needs its own star if you want it to be a pointer variable. That's why when I make pointers, I usually declare them like I'm showing down here. I make the star and I hug it right up next to the variable name to try to make it clear to me or people looking at my code that that star just applies to the variable name. And I'll probably do that henceforth, even though I've been leaving a little gap there until now. This slide is really talking about a special pointer value called null. It's a constant. It's defined in a few places in the headers. One place is standarddef.h, but I think if you include standardlib.h, I think you also get it there. It's a constant that means a pointer that's undefined, or really a pointer that doesn't point to anything. I take back what I said a moment ago about undefined. We'll talk more about that later. But it's a way of assigning a value to a pointer so that it's clear that it doesn't actually point to anything right now. It's a lot like null in Java, except it's capital in C and it's not really a reserved word in the language. It's just a preprocessor constant. But by convention, null means this doesn't point to anything. If a pointer is set to, so the nice thing about null is just like in Java, any pointer type can be assigned to null. And you can test to see if a pointer is null. You can mark a pointer as not pointing to anything by assigning it to null, like I'm showing up here, and then you can test it. The nice thing is null evaluates to false. So if you've got a pointer that may or may not be null, you can treat it as a truth value if you want. And if it evaluates to true, it points to something. If it evaluates to false, it doesn't point to anything. So quickly, you can assign pointers to null, you can test to see if they're null or not, but that's about all you can do with a null pointer, kind of like a null reference in Java. If you have a null pointer and you try to dereference it, you try to talk about what it points to, that's probably going to crash your program. It officially has undefined behavior. Who knows what might happen if you try to follow a pointer that doesn't really point to anything. But you should be careful about accidentally trying to use a pointer that hasn't been defined or that's marked as a null pointer. Questions before we move on? All right, so I'm just sneaking in this one special pointer value. We've already said something about what pointers are useful for. We said for some parts of the language, you have to use pointers. In a moment, we'll start talking about files, and that's one reason we're learning pointers now. To work with files, you have to at least know what the pointer notation means. They're also C's mechanism for pass-by reference, and that's what we're going to talk about next. You probably guessed that already, because one of the times we've talked about pass by reference is when we have to call scanf. And most of the variables we might want to fill in for scanf, we put ampersands in front of them. And I probably haven't said it yet, but that's the same ampersand we're talking about right now. It's really the address of operator. When you call scanf, you give it the address of all the variables that you want to fill in, and then it can use that address to go get to where those variables are stored and put something else in that memory. The nice thing is now we can do this ourselves. We can use exactly the same syntax to call a function and make it work via pass by reference. And the way this works, and again, when I say pass by reference, we're giving it a variable, but we're giving it in a way so that it can look at it and change what's in that variable. And by passing the address of a variable, that would let us do that. So that's how this mechanism works in C. I wanted to show a simple function that uses pass by reference, but it's one that we couldn't write without some mechanism for pass by reference. And we'll start with a swap function. Swap would be handy if you were writing a sort algorithm or something, if you found two elements and you want to exchange them for the sort to work. So we're going to write a function called swap. You give it two integers, but instead of passing them by value, instead of just giving copies of the integers, you'll have to tell me the address of the two integers. So I made two parameters here, but I made them both pointers to int. If you look inside the function, so the picture over here shows how this is supposed to work. Inside the function, x and y are both pointers to two different integers. If I want to exchange them, I can go get what x points to. That's what the star is. Give me the integer that x points to. Give me a copy of that integer. And then I can take what y points to and put it in the space x points to. Sorry, I didn't say the part. Save that in temporary variable up here for what you get from x. Put it whatever y points to into whatever x points to, and then take that temporary and put that in whatever y points to. So for all those stars sitting out in front of these variables, that means I'm following these pointers to the things that they point to. And that's kind of the standard sequence of operations you would do for swapping two variables. But you're doing it here via their addresses rather than just via their values. When you call this function, you have to be smart enough to give it the address of two integers. So since it expects two pointers, you have to use the address of syntax when you call it. A nice thing about this is if you messed up on this, if you just tried to pass it A and B, the type checking from the compiler would catch that. You'd be trying to pass in two integers, and the definition of the function says it expects two pointers to an integer. So a mistake like that wouldn't last very long. The compiler would notice it and wouldn't compile your code. Yeah.
Regarding these pointers, what would be the difference of just like for your void swap function, instead of making those pointer parameters, just making them like an unsigned int, seen as they just hold an address? So, and then when you're using the ampersand, you're just passing the address to like an unsigned int variable that should have enough space to hold the address, and then just reference that address that way instead of going through using pointers or this other type.
So the question is, could I cheat, or could I sneak a pointer into another type of variable as long as I knew that that variable was big enough to hold a pointer? And you could do that. But my question would be, why would you want to do that? It's going to take a lot more typecasting to actually use that. And you start risking, well, what if this was moved to a system where the sizes weren't what I expected? It might not work anymore. Like, let's say you moved it to a system where a pointer was bigger than an unsigned int. Well, you can still try to do those casts to make that work, and it'll compile, it just won't work. So I think, especially if you know something about the system you're coding for, you can make tricks like that work. I've probably done it, but I'm not proud of it. I would say it is safer and it's easier to write portable code if you try to use the type system that the compiler makes available to you. Although, like I said, I've done sneaky things like that before. Other questions? All right, so this is our first example of pass by reference, and we are going to use this throughout the rest of the semester. This is a nice thing, I claim, because it's not really something Java has. In Java, certain types automatically get passed by reference, certain types automatically get passed by value. And in C, for the most part, you can choose what you want. If you want to pass by reference, you pass the address of a thing. If you want to pass by value, you don't pass the address of a thing. You just pass the thing. And for the most part, you can do any type like that, except say arrays. Arrays are always passed by reference, kind of like they are in Java. This example, we're passing 2 parameters by reference, by address, but I didn't want you to get the idea that it's all or nothing. You can pick which parameters get passed by value and which ones get passed by reference. Here, I made up a function clamp. You give it the address of an int and a bound. And the idea is if that int is bigger than the bound, it'll pull it down to whatever that bound is. It'll lower it if it's too big. So for the variable that it's supposed to change, it seems like I have to pass that by address so that the function can change it. But I'm never going to try to change bounds, so I just pass that by value. So x is a pointer to some value held by the caller, and y is just a plain old integer value. Inside the function, if I want to compare x to the bound, I have to dereference x. Or really, if I want to compare that int to the bound, I have to dereference x. And then I can compare it to the bound. And then if I have to change it, I have to do the same thing. I have to look at the int x points to. When I call it, I have to give it the address of a real int as the first parameter, but I can give it any old integer value as the second parameter, including just a constant. So realistically, as you're designing code, you're going to think about which parameters need to be passed by reference, which ones you can pass by value. A common mistake that I see, especially in people getting used to C or if their C is a little bit rusty, is they try to make the compiler happy. And they assume that whatever error message they get from the compiler, they just need to make that error message go away. So I've seen people write code like I'm showing here, and this is deliberately bad code. Same clamp function up here. But let's say you called it and you tried to pass in just a plain old int as the first parameter. The compiler is probably going to say, you need to pass in a pointer to an int as that first parameter. So I've seen people say, oh, I need a pointer to an int. I'll make p a pointer to an int, and then I'll pass that in. And that'll make the compiler happy, but it's not going to make your program happy when it's running, because if you just declare a pointer p like this, and you don't actually make it point to anything. Now, that's what this little squid over here is supposed to show. That's an uninitialized pointer. And like any uninitialized variable, at least any uninitialized stack variable, if you didn't give it a value, who knows what garbage value it might start out as. And all these arrows are saying, well, who knows where this pointer points. If you call this function with an uninitialized pointer, well, it's going to get a copy of your uninitialized pointer. So in this clamp function, it got whatever x you passed in. So it got whatever pointer you passed in. So its x points to who knows where. And when it starts looking at where it points, when it dereferences it and tries to look at the int it points to, and especially when it tries to change the memory that it points to, it's probably going to crash your program. Although officially, who knows what's going to happen? It depends on where that uninitialized pointer happens to point. So again, this would be undefined behavior. If you were lucky, it might not crash. Well, I don't know. I was going to say if you're lucky, it might not crash your program. But since it's a bug, you'd really like it to crash your program right away so that you could debug it. You're just not guaranteed that it's going to do that. So like I said, I've seen this kind of mistake a lot, and it's usually people who are just trying to respond to a compiler message. Pointers give us a way of doing pass by reference, but it's really implementing pass by reference using essentially a pass by value mechanism. We're just passing a value that happens to be a pointer. And that's what this silly program tries to show off. By choosing to pass a pointer to a thing rather than that thing itself, we can get a pass by reference behavior or something that works like pass by reference. We'll still call it pass by reference, but the way we do that, the way it's implemented is by passing pointers. If we wrote a function, and that's what I'm trying to show off here. I wrote this function Hulk smash, and it's trying to show that a function that takes two addresses is really just getting copies of those addresses. Down here in the caller, I make a couple of variables A and B. I make a couple of pointers that point to each of them. So before I call Hulk smash, I think of memory as looking like this. I got two pointers, one pointing to A and one pointing to B. And then I call this Hulk smash function, and I give it my two pointers, one pointing to A and one pointing to B. So when this function wakes up, it has its own parameters, X and Y, and X gets initialized to point to A, and Y gets initialized to point to B. And then inside the function, I try to destroy those pointers. I set them both to null, and like we said, I can set any pointer to null. When I set them to null, well, I'm really just setting X and Y inside this function to null. The picture shows the effect that's going to have. X and Y are both null pointers now. And we'll use the same notation you're probably familiar with. We do a little pointer pointing down to indicate that's a pointer that points, that's null, that has a null value. But if you look down here in the caller, well, their pointers, A pointer and B pointer, didn't get changed. X and Y were just a copy of those two pointers, a copy of those two addresses. So down here in main, if we try to use those two pointers, it's still after we return from the function. They still work just fine because Hulk smash didn't actually change the caller's pointers, it just changed its copies of those. So far, we've been talking about pointers as parameter values. You can also use pointers as return values. We'll revisit this later. That's something to be careful about because you got to make sure that a pointer you return still points to something, that the thing it points to still exists after you return. But here's one way you could use it. If you had a list, say a global list of variable or of integers, and you wanted to be able to look up stuff on the list, like you wanted to be able to find a particular value, you could write a function like this. You give it a value, it looks through the list for that value, and if it finds it, it returns the address of that value. So it returns not just a copy of the value, but it returns a pointer to that value, which is kind of nice, because like I've said a couple of times, you could use that pointer to look at that value, or here you could change it. You could follow that pointer and change whatever element of this list you just looked up. If you wanted to call it, you could call it like this. It would find a copy of the first 30 on that list if it existed. Otherwise, it returns null. And this will work just fine. I guess in the caller, you have to be careful to make sure if it returns null, that you don't accidentally try to dereference a null pointer. But this will work just fine. Questions before we move on? We've really talked about our first example of functions that take pointers as parameters and here that return pointers as return values. We've been using silly values as pointers so far. I've drawn little pictures of memory and I've said, pretend this thing lives at address 12. And that's the idea, but if you looked at a pointer value, you probably wouldn't see a number like 12 in it. You can print out the value of a pointer. We haven't seen it until today, but this %p is a conversion specifier that'll print out any pointer value. It prints it out in hexadecimal in base 16. And if you're running on a 32-bit machine, a pointer value will probably look something like this, 8 digits of hex. If you're running on, and nowadays you're probably running on a 64-bit machine, pointers are a lot bigger. They're 16 digits of hex, because that's really what these things mean. A 32-bit machine means the address space takes 32 bits to describe an address. So a pointer is going to be 32 bits worth of hexadecimal. On a 64-bit machine, a pointer is going to be 64 bits worth of hexadecimal. So realistic pointers have, well, I won't say nonsense looking values, but they'll have a big value in hexadecimal, not tiny little values like the 12 and 6, or 26 we've been using so far. Pointers, so one thing to notice, and this is kind of like the question we got a moment ago, all pointers on a system are generally the same size. So on a 64-bit machine, all pointers are 64 bits in size. They're 8 bytes in size. But they don't all behave the same, and the compiler doesn't treat them all the same. And that's what I'm going to show, that's what I'm going to try to show next. You already know that the C compiler will kind of freely convert between numeric types without even requiring a cast. So you can assign a float down to a char if you want, and the compiler won't complain. So it will automatically convert integer types. But even though it's generally very lax on conversions between integer types, it's very uptight on conversion between pointer types. That's what I'm showing here. I make a char, a float, and a short, and then I make 3 pointers and set them each to point to their type. So a char pointer pointing to a char, float pointer pointing to a float, and so on. And then after I've done that, I try to sneak in and change the type those pointers point to. I try to take the address of the char and put it in a float pointer. I try to take the address of the float and put it in a short pointer, and so on. And the compiler is not going to like that. It's going to complain because the pointer types don't match. Even though it would happily convert a char to a float, it won't convert, at least without a cast, it won't convert a char address to a float. Sorry, I'm hearing a weird noise in my room and I don't know where it's coming from, but I'm going to keep on talking and I'll hope it goes away. It's not my laptop. Here's why. So we started with the idea that all pointers are the same size, but they don't all behave the same way. Sorry, I'm worrying about that noise. Maybe it's something outside. All right, apologize for getting distracted. So we've got, yeah, I apologize that I keep getting distracted. I just want to make sure nothing bad is happening. All right, I made the point that pointers are all the same size. So if you had a pointer to a char and a pointer to an int, those would both be 8 bytes in size. You can think of, and that's what I'm setting up here. I'm setting up a char. I'm setting up a pointer to that char. And then I'm using that pointer to change the character. So C started out with an H in it. And then I dereference the pointer to that C and I put a J in it instead. And I do the same thing with an integer pointer. The thing to notice here is a char pointer, since it points to a char, if I follow it and change the thing it points to, I'm really only changing 1 byte of memory. How does the compiler know to change just 1 byte? Because of the type of the pointer. If it's a char pointer, it points to a 1 byte thing in memory. And if you dereference it and change that thing, then you're only going to be changing 1 byte in memory. Whereas an int pointer, well, an int is 4 bytes in memory. So if you follow that pointer and change the thing it points to, you're changing 4 bytes in memory. And this is why the compiler is very uptight about changing pointer types. You can do it. You just have to make it clear that you want to. So here, same kind of code. I make a char and an int. I made a couple of pointers that could point to those things, but I switch them and make them point to the wrong thing. So I take the address of the int and I use a cast to say, pretend this is really a char pointer. And if I do that, the compiler will let me do this assignment. Same thing with the char. I take the address of a char, say pretend it's an int pointer, and put it in the int pointer. And then I do the same thing. I dereference those pointers, and I put 2 different values in them. But here's what you're going to get in this picture. When you follow the int pointer, and you change what it points, or you change the contents of the memory it points to, you're going to be changing 4 bytes of memory, because an int pointer should point to a 4-byte thing. Well, that means you're going to be writing past the end of that 1 byte char and into who knows what memory, probably other stuff you've got stored there. The char pointer is maybe not as dangerous, but if you do the same thing and follow the char pointer and change what it points there, you're really only changing part of that int. You're only changing its first byte. So this is why the compiler is uptight about pointer types, because if you start mixing them up, it's an easy way to accidentally overwrite memory that you didn't want to, or change just part of a thing. I've got some examples that try to show this, and we're really just trying to get used to what pointer operations might make sense and which ones the compiler is going to get upset about. So here, just to play around, I make an int and an int pointer with names that hopefully are easy to remember. I make a double and a double pointer, and a char and a char pointer. And then down at the bottom, I've got a bunch of operations, and I just want to talk about which ones might do what. If I take and so pretend we initialize these. I didn't show the code for that, but pretend we give them all values that are meaningful. If you take what the char pointer points to and dereference it, so go get the character it points to and assign it to an int, that's what I'm doing here. Is that okay? Well, I've got answers to all of these. That's okay. You're taking a char, it's just you're getting that char by following a pointer, so get the character that this pointer points to and assign that to an int. Well, the compiler's happy to convert a character to an int, so this is just fine. But this next one is not. If you take the address of an int, the compiler wants you to hold that in an int pointer, well, not a double pointer. So the pointer types don't match here. The compiler is going to complain if you try to do this. This next one works just fine. If you take a double pointer and you go get the double it points to, that's what the star does, and you try to assign that to the char that this char pointer points to, again, you're converting a double to a char, and the compiler's happy to do that. But if you try to take the address stored in int pointer and try to assign that to the address of an int, the compiler's not going to like that. Now, this is kind of for a different reason. One of them is you can't assign to the address of a thing. You can ask for the address of I and use that in things, but you can't change it. You can't ask the compiler to change where an integer is stored. Questions before I move on? I've got more examples. I've got a lot more examples. We won't talk through all of them, but I've got a lot more examples that try to show what pointer operations make sense and which ones don't. To talk about these, and we'll try and talk about these real quick, I make a couple of integer variables, and I make a couple of pointers to each of those integers. So px points to A and pointer y points to B. And then I just show off operations that are legal. So you can follow a pointer and assign it to an int. We do that all the time. You can take a constant integer value and put it in the thing a pointer points to. You can take the integer value out of a variable and put it in a thing that an integer pointer points to. You can follow two integer pointers and get the thing the integer one of them points to and put it in the memory the other one points to. That's just fine. You can take the address of an integer and store it in a pointer that's made to hold the address of an integer. That's fine. You can copy a pointer from one pointer variable to another as long as the pointer types match. All these operations make sense. All of these operations don't make sense. So just like here is a whole page of things you could legally do with pointers, here's a whole page of things that you can't legally do. We won't talk through all these, but maybe I'll do the first three of them. Same setup up here, same variables, same types. Here I'm trying to take the address of the number 35 and assign that to a pointer to an x. Well, a pointer to an int. 35 is an int, but constants don't have addresses. They're not stored in a particular place of memory, so you can't take the address of 35. Next line. Here I'm trying to take a number and dereference it. Well, pointers are numbers, but The compiler doesn't like you taking just a constant and pretending it's a pointer. For one thing, it wouldn't even know what type of pointer it's supposed to be. So you can't dereference a plain old number, you have to dereference a pointer unless you're willing to do some casting. Same kind of thing is happening on this next line, it's just in a different form. I'm trying to take just a plain old number and put it in a variable meant to hold a pointer. Now the compiler, unless you're willing to do a cast, it's going to say 35 is an int. It's not a pointer to an int, even though, again, pointers are just numbers. Unless this 35 has the right type, the compiler won't let you do this assignment. I'll encourage you to take a look at the rest of these and try to get some familiarity with what pointer operations make sense, and for this slide, what pointer operations don't make sense. We've been using these pointer operations a lot without talking about their precedence. Here I'm showing them in the precedence table. Star and ampersand are both, you can think of them as, they are unary prefix operators. So their precedence is just like any of the others, like logical negation or the size of operator or pre-decrement. They have pretty high precedence. They're really in the second highest precedence category. So that, at least that's easy to remember. And as we start writing more complicated expressions, that's probably worth remembering. They're pretty high precedence, but lower than things that come after their operand. We now have a small handful of type operators. Star, I've already made the point that it does a couple of jobs. You already know star does multiplication. If you put it between two operands, it tries to multiply them. If you put it in front of an operand, it's the pointer dereference operator. And it also works like a type operator for defining new types. We got a couple of type operators already, or I guess we've got at least one, square brackets. If you put square brackets after a variable, you're saying you want an array of some type. So we can use these in combination to start building really as many types as we want. And I wanted to show kind of what we get, and I want to talk about how these operators might interact if you start combining them. So obviously, if you declare a variable p here, this is a pointer to an int. It's the kind of thing we've been doing for the last 20 minutes. If you put square brackets after the name of a variable, you're making an array of ints. If you put up 2 stars in front of a variable, you're making a pointer to an int. What if you combine these? So here I've got AP, and in the front, I'm saying I want it to be a pointer. And on this side, I'm saying I want it to be an array of 10 things. It seems like I could get 2 things when I say this. I could get an array of 10 pointers to ints, or I could get a pointer to an array of 10 ints. Which one am I going to get? Well, to understand that, we need to know how to read types in the language C. And this will also tell us how to make types that we want. In C, even using this small collection of type operators, we can start defining interesting types. How do we read those types? Really, for the one that we just talked about, how do we tell the difference between an array of 10 pointers or a pointer to an array of 10 ints? Well, there are 2 simple rules for reading types, and I've listed them here. If you've got a variable declaration and you want to know what it means, I would start, what I say is start at the name of the variable and work your way out, respecting the precedence of the type operators. So that's why for a guy like PP, I read it as, well, PP, I'm starting at the name of the variable, is a pointer to an int. So I read the star as pointer to. So PP is a pointer to an int. How about AP? Well, is it an array of pointers or is it a pointer to an array? Well, the rule says respect the precedence of the type operators, and fortunately, the type operators have the same precedence as the regular operators that they look like. And if you remember from a couple of slides ago, square brackets, array indexing has higher precedence than star. So it would go first. AP would be an array of 10 pointers to ints. And with these arrows down here, I'm trying to show what I'm doing with my mouse. I'm starting at the name of the variable and I'm working my way out, respecting the precedence of the type operators. Questions before we move on? We've got a couple of type operators. I wanted to sneak in one more, a way of defining types, and it's the word const in C. In C, const means don't let me change this thing during its lifetime. It lets us define new types, but it kind of restricts what we can do with variables of that type. A variable like A is just a plain old int, and once you make it, you can change it. You can put a new value in it. But for B, I snuck in the word const. And what that means is don't let me change this thing during its lifetime. You can read it following the same rules we just did. B is a constant integer. So once you make it, the compiler will complain if you try to change it. It gets set to A+1, but you can't change it once you make it. I like putting the const here because it reads better. It follows the rules that I just described for reading. So B is a constant integer. You can't change it. But in this case, you can also put the const out in front, and it means the same thing. And most people write it that way. And really, I often write it that way. But it reads better. It follows the rules I'm describing better if you put it here after the type. So const, again, means don't let me change this thing during its lifetime. Java has a keyword const. When they defined the language, or when they started defining the language, I think they expected to use that. It's still a keyword, it's still reserved. It still doesn't do anything in the language, and it probably, at this point, it's probably never gonna get used in the language. Const means don't let me change this thing during its lifetime, but you can still do what I'm showing here. I've got a for loop. Each iteration of the for loop, I is changing. Each iteration I make a new variable C, well, that's declared const, but every time it gets created, it gets a different value, I plus 10. And this is perfectly okay because C is getting made every time through the loop. Every time it gets a new value, since it's const, you couldn't change it down here in the body of the loop after you make it, but each time around, when C gets created, it can get a new value. How is const useful? Well, it's useful when you use it in the context of pointers. Here, and really it's useful when you pass pointers to a function or when you return pointers from a function. We'll get to that in just a moment, but first let's show how it works when you use it with pointers. So here I'm making 3 different integer variables, and I'm making 3 different pointers that point to each of them. X points to A, Y points to B, and Z is going to point to C. But I snuck in the word const here in these variable declarations. You can read them. X is a pointer to a constant integer. Well, it's a pointer to a constant integer, so you can't change the integer. You can't change the thing it points to, which means this line of code won't work. It won't compile. If you say, take X, give me the thing it points to, and put something else in there, the compiler is going to complain because you said, I want X to be a pointer to a constant integer. So it won't let you change the integer it points to. If you take the word const and you move it here, well, reading it, Y is a constant pointer to an integer. That means you can change the integer, but you can't change where the pointer points. It's a constant pointer. So you can't do this. You can't take Y and make it point to C instead of B, because you said you didn't want to be able to do that. You didn't want to be able to change where it points. You can have both. Z is a constant pointer to a constant integer. And that means you can't change where Z points. You can't make it point to a different integer. And you can't change the contents of the integer it points to. Like I hinted at a moment ago, this shows how this works. But even this, why would you want a pointer that you could do less with, where you restricted what you could do? And here's why this is handy. It's handy in the parameters to a function and in its return type, because it lets the function say what it might do with your pointer. Let's say I have a function f, and it says as my parameter, I want some pointer to a constant double. What that means is you're going to give me the address of a double, but I promise I won't change it. I just want to see it. I want to be able to look at it, but the pointer you're going to give me, I'm declaring as const. And again, that means the compiler's not going to let me change the double it points to. You could write a function like this. This obviously computes the area of a circle given its radius. If you give me the radius as a pointer, well, I can dereference it. I know there are a lot of stars here. These two are multiplication, and the one in front of the pointer are dereference. So go get the double d points to, go get the double d points to, multiply those and multiply that by pi and return the result. And this will work just fine. I'm dereferencing the pointer, but I'm not trying to change the double it points to. So here you can think of this function type as a promise for what the function might do with that pointer. As far as type conversions, you can always go from a plain old pointer to a const pointer, or a pointer to a constant thing, and that doesn't even require a cast. That conversion happens implicitly, because it's kind of like you're going from a pointer where you could do a lot of things, you could change the int it points to one where you could do less, where you promise you won't change the int it points to. So going in this direction is implicit, but going the other direction is going to require a cast. The compiler won't let you do that unless you make it clear that you mean to do it with a cast. In general, we're going to start trying to use const in our programs. And that means if you've got a function and it takes the address of a thing as a parameter, but you don't plan on changing the thing, you should put the word const on it. Same thing with the return from a function. If you return a pointer, but the caller needs to not change the contents of memory that points to, you should stick the word const on that. And then the compiler will start trying to make sure that you don't cheat anywhere, that you don't try to modify something that was declared as const. This is what I'm talking about. If you call a function and it says, I promise not to change the value this pointer points to, and then you sneak in and try and change it anyway, the compiler will catch that and complain about it. But you can cheat if you want, and I kind of hinted this a moment ago. Since const is really just part of the type of a thing, you can get rid of it with a typecast. So if you wanted to be an evil function, and you said, oh, give me a pointer to to a double, I promise I won't change it. And then inside, you could take that pointer to a double, you could cast it to you could take that pointer to a const double, and you could cast it to a plain old double pointer, and then dereference that. The compiler will let you do that. This is called casting away const. And it may make you think, well, const is worthless if you can just get rid of it whenever you want. But I think that's the wrong way to think about it. I wouldn't think of const as a security measure. It would be nice if it was, but instead I would say think of it as a way that programmers can communicate between each other. Programmers that are not trying to mess with each other. It's a way for a function to say what it plans to do, and it's a way for someone calling that function to understand what that function might do. And that gets us to the end of our discussion, our first day of pointers. We're going to revisit this pointers a couple of times throughout the semester, because you can do a lot more with them than what we've talked about so far. Mostly we talked about how they work as a mechanism, and we talked about how they can be used to implement pass-by reference. And now we can use that in our own programs. There are a bunch more things we can do with them that we'll learn about soon. Here's where we should have been at the start of class today. And I don't think we're necessarily catching up, but I don't think we're falling further behind yet. So I'll see if I can catch us up a little bit today. Here's what I thought we would talk about. We're going to talk about file I/O. We're going to talk about parsing with scanf. And then at the end, I don't think we'll get to this, but hopefully we'll soon be able to talk about strings a little bit. So far, we've avoided using files directly. We've done files by doing IO redirection, but now that we know about pointers, we can start working with files. Said differently, working with files requires at least a little knowledge of the pointer syntax. So we can open files ourselves. We don't have to depend on the shell for that. But both for reading and for writing. Standard IO already includes support for working with files directly. So if you include that, you get the stuff I'm about to talk about. If you want to open a file, here's the syntax for doing that. There's a function fopen, and it expects two things. The name of a file you want to open, that's the first parameter, and that's just a plain old string. It will, if you don't give any other information, it'll look in the current directory for that file. You could give a full path name if you wanted to open a file in a particular location. And then the second parameter is, what do you want to do with that file? That's called the mode string. We'll see that on the next slide, but here with an R means I just want to read from the file. So I want to open it for reading. Fopen returns a pointer. There's a type called file in all caps, and you don't have to know what's in that type or what it means. All you need to know is a pointer to that type. A pointer to a file is how you keep up with a stream in C. And a stream is just the name for a file that you've opened. If you call fopen, it makes a new stream for you, and it gives it to you by returning what we usually call a file pointer, a pointer to a file object. Since it's a pointer, that's a handy way of knowing if this function works or not, or if you try to open something and you can't, maybe because it doesn't exist, it'll return a null pointer to you. So you could check that return value and see if it was successful or not. You can call fopen, and you can use this to get files for reading or writing. If you want to just be able to read, you put a quote R. It's a string. Even though this is just one character, it's expecting a string here, and we'll see why a little bit later. But R means I just want to read. If you used W, looks kind of like a capital W, but it should be a lowercase w. It means I just want to write to that file, and we'll learn more mode strings a little bit later. Questions so far? So fopen is our way of opening files. When you call it, you get back a thing that we usually call a file pointer, and that's your way of working with the new stream that you just made. What can you do with it? If you've opened a new file, how do you write to it? If you want to read from it, how do you read from it? Fortunately, there are functions for doing that are almost exactly like the functions we already know. Printf is for printing stuff to the terminal. Its good friend fprintf is for printing to files. C does not have function overloading like Java has, so all the different versions of printf and scanf have to have slightly different names. And that's what this extra F in front means. It means I want to print to a file rather than the terminal. fprintf is just like plain old printf, except it has this one extra parameter in the front. It wants a copy of the file pointer that you want to write to. So fprintf will print out same format string as regular printf, same arguments after that. It just needs this extra stream in front that says where the output should go. Same thing with scanf. Scanf is for printing to the terminal. fscanf will print to, scanf is for reading from the terminal, and fscanf will read from any file you want. You just pass it in as an extra parameter. The rest of the parameters are the same. So the good thing is, at this point, we know how to print to a file and read from a file. They're almost the same functions we've used. We need one other function, and that is in C, we have to say when we're done with a file. We have to call fclose to sort of give up that stream, to tell the standard library that we don't need to use that stream anymore. And the main reason for this, or I guess one reason for this, is internally, those streams are probably doing some buffering. If you print out a bunch of stuff, instead of actually sending it to the file right away, these streams will probably hold it in memory for a while. if you print a line, or if you print out some text and you don't have a \n at the end, it might not actually show up on even on the terminal, because it might be buffered in memory until you end the line that you're trying to print. So that's something to be careful about. For a file, if stuff is buffered in memory, it might not get written out to the file until you close the file with fclose. So be careful at any file that you open. You want to think about where you're going to eventually close that, because if you don't, we'll call that's called a file leak. And if you keep opening files and never closing them, you might not be able to open any more files. I've got an example program for that in just a moment. So here's a fragment of code that shows off some of what we've learned so far. This program reads a bunch of numbers from a file. I'll try to go through it quickly. Up at the start, we use fopen to open a file called numbers that we want to read from. We save that in a variable of type file pointer called fp. If that failed, we might want to write some error handling code. Remember, null pointer evaluates to false, and any other pointer evaluates to true. So if not fp is true, or if we got null from reading, that would, let me try and say that again. If fp was null, not fp would evaluate to true. So you can think of this as saying, if I didn't get a file, we could put error handling code there. And then I'm just going to read all the numbers and add them up. I've got a total variable for that. I'm reading a bunch of numbers just like we would with scanf, except I'm using fscanf. So I put in the file pointer as the first parameter. I read each number into val. I check to make sure I successfully read a number, and as long as I did, I keep reading. I add the result into total. I'm going to print out the total at the bottom, but before I do, I close the file I was reading from. So here's a simple example of how you could use the functions we just looked at to read arbitrarily many numbers from a file. Here's the other way around. If you wanted to write a bunch of numbers to a file, you could use fopen to open a file called output. Here I'm saying I want to write to that file rather than read it, so that's that mode string we were talking about. I should get a pointer back from this, so I store it in a file pointer variable. I check to see if it was successful or not. And then I go through and print out, I guess it's the area of a bunch of circles of different radii. I print those out as floating point numbers, one per line, but I use fprintf to send that to a file rather than the terminal. And then, especially here, since some of that might have been buffered, I definitely want to close the file before I'm done to make sure any buffered output gets flushed. Questions before we move on? All right, this will be easy. Remember when we first learned input and output from the terminal, we learned how to do it a character at a time, and then we learned the formatted versions. So we learned getchar and putchar, and then we learned printf and scanf. Well, going back, there are character by character functions for reading and writing to files. Getchar and putchar were for working with the terminal. fgetc and fputc are for working with files. They're just like these two up here. The names are even shorter. fgetc will read the next character from any stream you want and returns it as an int. Same rules as getchar. If you hit the end of file, you get back EOF rather than any legal character. But until you hit the end of file, you should get back codes for whatever the next character, or more generally, whatever the next byte is on that file. Same thing with fputc, you give it a character, and after the character, you give it the stream you want it to go to, and it'll send that character to the stream. Remember, the return value here is EOF on failure. So if we wanted to show off the use of these two, we could write a simple program to copy a file one character at a time. Here I do two fopens. I open a source file for reading. I open a destination file for writing. And then I'm going to go through all the characters in source. I'm going to call fgetc, getting the next character. As long as that wasn't EOF, I'm going to send that to the destination file. So this should run one iteration for every byte for every character in the source file, sending it to dest. And then when I'm done, I close both of these files. Questions? So we just learned two new functions and an example of how to use them.
Professor Sturgill, I don't know if I'm missing them, but the PowerPoint that I'm following along with doesn't seem to have these slides.
Doesn't have the ones that I'm talking about right now?
That's correct.
All right, I appreciate that note. I will fix that. I meant to update or check on that. It may just be, probably I moved these earlier and you've got an older version. I'll fix that after class. I'm sorry about that. And you probably don't have this function either, but I'll put in this slide. Input and output streams perform buffering. And for an input stream, you are guaranteed to have at least one character worth of buffer. And you can use that to put characters back on the stream after you've read them. This might seem like a weird thing to do, but it's awfully handy for parsing. If you're reading input and you get, let's say you're reading a string from input, you're reading a word. Now, how do you do that? You probably read a bunch of characters until you get the first character after the word. Well, you found the end of the word because you found maybe some white space after the word, but you didn't really want the white space. You just wanted the word. So it's handy to be able to take, so in general, when you're reading a thing, sometimes you have to read at least one byte past it to know that you've hit the end of that thing. Well, you didn't want to read that extra one byte. You had to read it just to know that you had hit the end. So you'd like to be able to take that back. You'd like to be able to give that byte back to the stream so that some other piece of code could read it. And that's what this function is for. UngetC is for taking the most recent byte you just read and putting it back on a stream. And I really mean putting it back into the buffer. This even works with standard input. If you're reading from the terminal, you can read a bunch of characters, and then if you read one character more than what you wanted to, or if you tell you got to the end by reading one character past the end, you can put that character back so other code can read it. It's not going to show up on the terminal again or anything like that. It'll just go back into the buffer, and then other code could read that later. This is handy for a lot of parsing applications. So I'll go ahead and introduce this now. I mentioned that if you open files and never close them, then we call that a file leak. And there are consequences for that. If you had a long running program and over it kept opening files and never closing them, then it would eventually not be able to open any more files. You would kind of hit a resource limit on that. And that's what this piece of code shows. It's a deliberately bad program that just loops. It's got an infinite loop here. Every iteration of the loop, we haven't learned this function, but we will soon. It makes up a new file name. And then it tries to open that file, a file with that name, for writing. So this will create a new file if it didn't already exist. And then it checks to see if that was successful. And until that fails, it just keeps looping, making more and more files until it can't make any more. And then that's pretty much it. It says if it was successful, so we'll see a trace of it successfully opening files until it can't open anymore. And then that's the end of the program. I've already compiled it. Let's give it a try. And I'm running this on a university machine. All right, there we are, opening file after file after file until we hit a limit. After we had opened 1,021 files, the operating system said, no more files. We hit a limit on how many we could open, and that's what I mean by a consequence of a file leak. If you're leaking files, eventually you're going to hit a limit like this. If you take a look, we just created a bunch of garbage empty files in my directory. I'll delete those later. I wanted to talk a little bit about that. It seemed kind of weird where we hit the limit. It was 1,021, which seems like an unusual number, but it's awfully close to a nice round number in binary. In binary, 1,024 is 2 to the 10th. We're 3 away from that. And the reason is, because when our program started up, and you know this already, we already had 3 files open, or we already had 3 streams. The 3 streams you're familiar with, standard in, standard out, and standard error, were already there when our program opened up. it looks like our limit is probably 1024 files. It's just 3 of them were open before we even got a chance to start opening files. You can make as many streams as you want, well, at least up to the limit, by calling fopen. But when your program starts up, you have 3 streams that already exist, and these are their names. There are essentially global variables named standard in, standard out, and standard error. And when you include standard IO, you've got extern declarations for those. So you already have access to those variables. So you can use these 3 streams just like any other file pointers if you wanted to use those for input and output and name them explicitly. Often you don't have to do this. You could print to the you could read from the terminal by calling fscanf standard in, and that would work just fine. And there's a shorthand name for this, plain old scanf. You could write to the terminal by calling fprintf standard out. There's a special shorthand for doing that. So either of these work equivalently. If you wanted to print error messages, well, you're going to have to use this slightly longer form, fprintf to standard error, but this would let you send error messages to the error stream. Why would you want to send error messages to a different stream? Because standard error gets redirected differently from standard output. So you could send your standard output to a file, but you could still let error messages pop up on the terminal. And that would kind of be nice. It means even if your output is going to a file, you can still see if something went wrong. So it's nice that we can redirect those separately. By using standard error, we can send error messages to this error stream. We just have to print out error messages like this. And we're not doing this on our current project, but we'll probably start doing this on future projects. If you want to print an error message, the standard error, you just, so say you try to open a file and you can't open it. You could print an error message to standard error by saying fprintf standard error, and then whatever error message you want. If you try to read an input that you were expecting and you can't successfully read it, you could print an error message the same way. So this gives us a kind of a typical way of handling errors and printing out, at least responding to errors with error messages. I mentioned that you can redirect standard error differently from standard output, and here's the syntax for doing that. You already know a greater than sign sends your program's terminal output to a file instead of straight to the terminal. If you use this notation, 2 greater than, you're saying, here's where standard error needs to go. And this will send any of your error output, any of your error messages to a file called error.txt. So running a program like this, its 2 streams are going to go to different files. If you wanted them to go to the same file, you could use this kind of goofy notation. This says, send my standard output to everything. And then this says, take standard error and send it to the same place as standard output. Output stream, or stream 1 is standard output. So this, again, kind of goofy notation says, send error output to the same place as standard output. This is all shell syntax. This isn't really C specifically, but if you're running on a Unix system, and especially if you're using a shell like Bash, this is the syntax that you're using. And if you're using a university machine or probably a Linux machine, your default shell is probably going to be Bash. All right, that's file input and output. I wanted to talk a little bit about the language that scanf supports for reading input, because there's a lot of stuff we haven't talked about yet about this. So let's see how much of this we can get through. This part you already know. If you want to read a string, if you want to read a word from input, well, %s will let you do that. And you can just pass an array of characters and it'll store the next token, the next word it sees in that array of characters. And we already talked about this. We already talked about how, well, the hazard here is this doesn't do any bounds checking because it doesn't even know how big your array is. So if the user typed in a really big word, it could buffer overflow your array and potentially crash your program. There's a syntax for limiting how much input you get. And here's what it looks like down here. You just have to put a bound between the percent and the S. And this 99 says, read a string that's at most 99 characters in length. It's kind of like the field width when you're doing output. But if you put a field width or if you put a number in the same place on input, it limits how big the input is. So if you've got a 100 character array, like we said, you can hold a 99 character string, and this is enough to prevent buffer overflow. This is just our first example of a wide class of syntax that you can use to tell scanf what to read when you're reading input. And I want to see how much of that we can cover today. We've got about 5 minutes left. So this limits how much you want to read, again, for preventing buffer overflow. Instead of reading an arbitrary string, you can tell scanf what characters to match using something called a character class. Instead of putting an S after the percent, if you put any set of characters inside square brackets, you're telling scanf to read a string consisting only of those characters. So here I'm saying, read any sequence of A's, B's, and C's in any order and store the result in this string. If you do that, it doesn't do the white space skipping anymore, but we'll show how to fix that. But this lets you pick what you want the string to be made of just by listing whatever characters you want. How could you use this? Well, if you had, same example as before, read me a string consisting only of A's, B's, and C's and store it here. If you had input that looked like this, you just get these red characters. B, C, A, B, B are in the set. X is not. So it's going to stop right there, and you're just going to get the first part of this input line. If you tried to read this, you're not going to get anything because this first character Z isn't in the set that you said. How could you use this? Well, like if you wanted to read just digits or here digits and a space, you could make a character class for that. And then this will read only digits and spaces and store them in the string. So if this was your input, it'll read everything up to this X. There's a space here. Well, that was in your set, so it'll also read that, but it'll stop right before this X. So this really gives you a shorthand way of picking exactly what you want to read based on a set of characters. If it was a big set of characters, like all the letters, it would be irritating to have to list them all. So scanf supports a shorthand notation for doing that. If you put a dash between a pair of characters, you're saying characters with any character codes between the first one and the second one. So capital A dash capital Z, remember those all have consecutive character codes. So this would match, sorry, all the capital letters have consecutive character codes. So this would match any capital letter. The dash is a shorthand way of saying anything from the first guy up to the last character. So this would match any capital letter. Down here at the bottom, if you wanted to match any letter at all, you could do that with two ranges. Lowercase a up to lowercase z and capital A up to capital Z. I also snuck in a dot here. So this would match capital letters, lowercase letters, or the character dot. So on input like this, it would match every ABC, lowercase is in the set, so is dot. XYZ, uppercase is in the set, so is the dot, but one isn't. So it would match everything up to that first one there. Questions?
On the other slide, it was saying
This first one?
Sorry.
Here.
On the other, it was saying something about noticing that there's no ampersand in front of the str, but I was just wondering why that is.
We talked about that at the end of, I think, lecture 8, and it's because ampersand is for pass by reference. Any of the primitive types are not passed, or they're passed by value by default, but remember arrays are automatically passed by reference. So we don't have to put an ampersand here to get it to pass this string by address. Again, because strings are always passed by address, because a string is an array. Did that answer your question?
Yes, thank you.
All right, and that got us to the end of our time. So we'll pretend right here is where we left off. So we did not cover this, but we did cover this. I'll try to update. We've got a study guide for the exam next week, so I'll try and update it based on how far we actually got. I'm just trying to catch us up a little bit, so I know I'm probably going a little bit fast to compensate for going slow earlier. I'll go ahead and stop recording now, but if people want to hang around and ask questions, I'm happy to take those questions.